Hello everyone, it's Mark Radwin again with another Google Earth Engine tutorial, specifically using the RadGEEToolbox Python package. And I am going to be going over how to assess turbidity of coastal waters using Landsat or Sentinel-2 data. So I have this Jupyter notebook kind of laid out, and I'll have this uploaded, and you'll be able to find it in the description of the video. And also as a reminder, the RadGEEToolbox package is something that I developed and put out there, and I'm just trying to gain some more attention as it's been really helpful for me in my own work, and I hope others can find it useful as well. And that package you can find on GitHub with all the information needed about the package. You can find the link to the documentation and learn how to install it. And I recently just came out with a new update yesterday, version 1.5.0. Of course, it probably won't be yesterday by the time this is uploaded, but I came out with some new features, including support for Sentinel-1, so synthetic aperture radar data, and I also added some more features such as getting data from transects and iterating on multiple transects over an image collection. But anyways, that's not the point of this video. The point of this video is to look at coastal turbidity. And I'm just going to quickly walk through this Jupyter notebook. I won't go too in depth on things, but if you have any questions, please let me know. So first off, you'll just want to open this up. You want to activate your environment. In this case, I'm using VS Code, and I've already done so. But if you're using VS Code, you can always check on your environments, and you can activate the one that you want to use. In this case, all I really have installed is RadGEEToolbox and GMap. So import the packages, initialize Earth Engine. You may need to authenticate. If so, just comment out the initialized line and then and uncomment out the authenticate line and authenticate it, enter the code. You'll get used to that. And I have quickly defined a region of interest for filtering the image collections. And essentially, this whole example notebook is going over turbidity at the Yellow River Delta in China. And to get this polygon, what I did was I go to code.earthengine.com, or .google.com, essentially the code editor that you would use if you were using JavaScript version of Google Earth Engine. And of course you can do similar with GMap, but I kind of prefer doing this way, where I come in the editor, I draw a polygon. In this case I have two. I'll show why the second one's needed later, but I have this first one, and I just drew it in the area of where I want to filter for imagery. So in this case, just a small area around the Yellow River and the Yellow River Delta. And then what you can do is you can go up here to this little blue icon, and it'll actually show you the code needed for each polygon. So essentially I just copy and paste this portion and add a parenthesis at the end to close it off. And that's what you see here for the region of interest called ROI. And then we want to state in the start and end date. In this case, I chose 2023, the end of March, and the end of June. So we'll run that, put that into memory. The next part is we want to now define the collections. I'm going to show how to do it for both Landsat and Sentinel. So essentially I defined a base collection called Landsat collection and a base collection called Sentinel collection. And from the RadGEEToolbox package, bring in the Landsat collection, define the start and end date. I specified a cloud percentage threshold so I don't get any cloudy images. And we want to filter all of these Landsat images based on a boundary, and that boundary is that region of interest I just showed you. So this whole line will get you an image collection of Landsat data between the time frame that we want, with low clouds, and only the location that we want. Next, we want to calculate it to turbidity. Now, to calculate turbidity, there is a multispectral index called the normalized difference turbidity index, and this is calculated by subtracting the green wavelengths from the red wavelengths. And the way this works, realistically, there's many other turbidity indices, but this one is pretty simple and it works. And how this one works is essentially turbid waters look more red. So by subtracting green from red, if it looks more red, then you get a higher value, but if it's clear water, it won't really look red at all, so the value will actually probably be negative. But in this case, what we do is we call in that Landsat collection we just defined. So we're saying take the Landsat collection, and here's a function from the RadGEEToolbox. It's called mask to water collection NDWI. So basically this will mask the imagery to water using NDWI, and then we specify the NDWI threshold. So we're not being super detailed here, we're just going to say 0. And then use the method property called .turbidity. So this will calculate the turbidity index, the normalized difference turbidity index for all the images in this collection. So essentially we've masked it to water, and then we've calculated turbidity. So we only are going to see turbidity values where there's water. Then it's nice to just have a list of dates, so call this Landsat dates, and just using the .dates property. And then we'll print that. And same exact thing for Sentinel. We're going to say the start and end date. We're going to classify or specify a cloud threshold. Going to choose the same boundary, but then there's additional caveat here is you can have some scenes that have quite a bit of no data in them, either just the geometry of the orbit path and the fact that each Sentinel swath is divided into multiple scenes. Sometimes some of the scenes get cut off, and there's also some weird things that result in no data values, so we can filter based on that as well. And because the region of interest that we chose is bigger than an individual tile from a swath or a single path of the satellite, we have to mosaic all of the images that are from the same date. So in RadGEEToolbox, I provide an easy way to mosaic images by date, just using this mosaic by date property. So .mosaic by date. That'll mosaic them. And note, when you do this, it does impact processing time, as Google Earth Engine servers will need to then mosaic the images before you can do anything with them. And that happens every time you call in an image from this collection. So this can add on a little bit of processing time, but not drastic. And same thing to calculate turbidity. We're just going to call in the Sentinel collection, mask it to water with NDWI, and calculate turbidity once again. And then we'll get another list of dates. So if we do this, see how fast Landsat processed because we didn't have to mosaic, but now with Sentinel we're waiting for it to mosaic all the images and show us the dates. And we see that there are a lot more dates for Sentinel, which is one of the pros of using Sentinel. Next, we want to make a map. Let's just kind of get a demo seeing what these things look like. So this first cell was focused on Landsat data, and in the package RadGEEToolbox, I also offer another functionality called Get Visualization Params. This makes it really easy to just get the visualization parameters for what you're looking for. In this case, we're using the Landsat satellite because you'll need to specify the satellite, the index type, and then you can even go further and specify min val, max val, or palette if you're using single band imagery. In this case, we're not using single band imagery, we're just saying Landsat, it's true color, and I kind of scaled it such that there'll be better contrast in the imagery. And I did the same for turbidity. I offer a way to get visualization parameters for NDTI imagery, and then stretched the data there a little bit. And I kind of just did this by trial and error. There's it'll be different depending on the environment and the time of year. And a useful little tip here is I like to use this, I just like to specify an index, because with the RadGEEToolbox package you can easily select any image from a collection using this method function called image grab, and you just need to specify the index. So essentially if you say 0, that'll select the first image in the collection. If you say -1, that'll select the last, and so on. So in this case, we're going to just show the first image in this collection. We're using the visualization parameters that I've just defined above, and we're giving it a name. And it's always nice to see the date of the image we're looking at, so we're going to print the date of this image, and then we're going to add it to the map. And we're using Gmap to make the map here. So here's the Yellow River Delta, and you can see the turbidity values and the yellow to browns, where these browns are suggesting there's more turbid waters. And now let's look at that in a little more detail. Let's turn off the turbidity index, and you can see what the water looks like normally without being processed. And then you can see that the turbidity kind of captures very nicely where all these turbid sediments are coming out of the delta and where the water is pushing it around. So next we'll do the same for Sentinel. Again, bringing in some visualization parameters for Sentinel-2 and specifying min and max vals to just kind of stretch the imagery to look best. Using index of 1 here, as we are going to use the April 1st date from 2023. And again with this doesn't process as quickly because it's having to mosaic the images on the fly and then grab the image that we're interested in. So here's what the Sentinel-2 imagery looks like. Turn off turbidity, you can see what the water looks like. Turbidity, you can see it captures where those more yellow-brown waters are located. So cool, we can just kind of investigate the turbid waters. Let's zoom in. And you can also see that the masking has done a nice job delineating the water front from land. We can see that the river itself is very turbid. And then we can see the sediment plume, similar for Landsat. For Landsat, it's almost a little cleaner because we didn't have to mosaic. But you might be saying, okay, that's cool and all, but realistically, might want to do a little bit more with that. For example, let's mask the water to only turbid pixels. So you can do some assessment and you can find the value that really kind of separates turbid waters from less turbid or not turbid waters. In this case, just after a little bit of analysis for Landsat data, I chose a threshold of negative 0.05. For Sentinel data, a threshold of 0.15. And this cell block right here, basically what it's doing for both Landsat and Sentinel is I'm calling in the turbidity collection and I'm turning it back into a Google Earth Engine collection, which you can do easily by just doing dot collection. And then we're going to map a function off to every single image where we're taking an image, we're updating its mask by selecting the turbidity band, and we're just going to get values above the threshold. Same thing for Sentinel, grabbing an image and just getting the pixel values above the threshold. And then we're going to turn it back into a RadGEEToolbox object so that we can keep on using some of the nice other functionality for mapping. So we'll run this. And then we can map it out. So let's look at the Landsat imagery where it's just going to show turbid pixels in the water. So now we can see, okay, now we're just looking for where there's really turbid waters. And you can see if we would have raised the threshold, we could, if we lower the threshold, we could include more of some of these turbid waters. But if we turn this off, get a look at the true color imagery, you can see that the waters it's detecting and classifying are definitely a bit more bright and more turbid. So we'll do the same for Sentinel. Let's just run this. We're going to just, all we're really doing is we're just adding those, once again, basically additionally masked data and essentially classified data using threshold to the map. And we can see again here that we just are getting the most turbid waters in the scene. And one of the reasons why this is useful is, like I said, it's kind of like a classification scheme. You can use this method of thresholding to make maps, honing in on materials of interest, in this case, water pixels of interest. But it also is nice because you can then use these pixels to calculate surface area of turbid water. So you could essentially look at through time, when were the most turbid times, and what sort of surface area did the turbid waters encompass. So I'll show how to do that next. We're going to define another region of interest for a larger area to kind of capture this whole region, to see just within this area, what's the surface area, what's the area of turbid pixels. To do this, once again, I just drew a geometry, a larger geometry, and copied and pasted the information about that geometry from the Earth Engine editor into Python, which you can see here. Ran that. And then I won't run these just for time's sake, or for Landsat I could because it only took 0.2 seconds previously. But essentially, to get the pixel area, or the area of the pixels that are turbid water, you call in the collection that we had just previously done. So we masked the turbidity values to just the most turbid pixels. And then in RadGEEToolbox, there's another functionality called pixel area sum collection. So this will calculate pixel area for an entire collection, and it sums up the pixel, the area for all the pixels that meet your specifications. In this case, you can give it another threshold, so that essentially, if you didn't want to use the thresholds we use to mask, and you want to use a more restrictive threshold, or if you don't want to go through that last step, you just want to maybe take one of the images like this, that you're dealing with all of this water and you already know the threshold you want, you can use that as well. But we specify the band that we want to use for calculating area. It's called NDTI. And then we have the next to ROI, which is we call it area for stats. And like I said, you can have, there's more options here. You can choose your threshold of interest. You can choose the scale, the pixel size that you want to use. You can use max, and you can set the max pixels. And when this processes, it will store the area value in meters squared as a property of the image. So once you run that, we can then now make a new variable storing this data. And the way you can get to that data is by calling in what we just made, the ls turbidity area. And then you would do, and by this point, this turns it back, this pixel area sum collection function turns it back into a Google Earth Engine object. It's not a RadGEEToolbox object after that. So what we can do is we can call .aggregateArray, which will basically give you a list of some image property that you're interested in. We're interested in the image property called NDTI, because that's how the pixel area sum collection stores its values. And then we put .getInfo, which will give us the values. It will give it in a client side readable format instead of server side. And then we can print those, and you can see that for the 4 Landsat images in our time frame, those are the areas, surface areas that we can calculate and retrieve from the imagery. And if you plot that out using matplotlib, it looks something like this. Nothing too crazy. We only have 4 values. And then you can do the same for Sentinel. So same exact process using pixel area sum collection, the same region, basically the same exact code. And we have more images for Sentinel. As you can see, we have more images in the list. And we can also plot those using matplotlib. And you can see there's more variation through time, maybe some precipitation events, etc. So this is a really useful way for you to assess coastal turbidity, and some of the cool ways you can use RadGEEToolbox to really minimize the coding effort needed to do all this. So yeah, I hope this is somewhat useful, and I plan on providing more tutorials. I know I had said that previously, months and months ago, but you know, things are crazy for a PhD candidate, and I really only have the time to do this every now and then, and I was feeling a little bit inspired to do some more work on this, especially after updating the package. So I definitely have a list of tutorials planned, so keep your eyes peeled and let me know if there's anything you're curious about me making a tutorial on. Yeah, and thank you.